Okay, so we have looked at the chain rule, probably the toughest and most powerful differentiation rule, and from it picked out a nice technique for tackling anti-differentiation or integrals. We're going to do the same thing with the product rule. We're going to pick at the product rule for differentiation and come up with an anti-differentiation rule called integration by parts. Okay, so I've got here the product rule. So if I have two expressions, both of them differentiable, and I have their product, then the derivative of their product is this sum where I take the derivative of one of the factors and leave the other factor alone. So we're going to do much like we did with the other technique. We're going to integrate both sides, and that's going to undo some of the differentiation. So let's integrate both sides. So the integral of this side is equal to the integral of the anti-differentiation on this side. Okay, now this is pretty clear cut. We've got a integrand here that is the derivative. Well, we've got the derivative of a function here, and then we're taking the antiderivative of it. So we know what that's going to come out to be. All right. Now, I should have a plus c here, but I still got integrals left, and I'm going to just wait till the end, to my final integral, before I throw in the constant. Okay, so there's a constant there. Now, what I want to do is to set this up so I start with an integral, and then that's equal to something else that either it would be nice if it just equal to an answer, but it's not, but something that is different from the integral I had, so that maybe I can be clever and transform my integral into something simpler. So I'm going to start with this integral right here. This is the integral I want to pretend like I'm starting with, and so I want to pull this to the other side of the equation. Actually, I'm going to pull this to the left because we like to read left to right. So it's going to be this integral is equal to the product of these two functions minus this integral. Okay? And there we go. Now, what I want to do is make this as simple as possible. So I'm going to drop back and use one of the techniques that we were using with the substitution method. I'm just going to stick in one single letter for f of x and for g of x, and I'm going to use u and v. So for f of x, I'm going to have u, and everywhere I see a g of x, I'm going to put a v. So what do we have? Well, we get this. Okay, now what am I going to do about g prime of x dx and f prime of x dx? Well, we talked about this with the substitution method. One of the reasons why I've put these two together and the substitution method coming first is that this is a differential. If we think of g as v, then the rate of change of v with respect to x over times dx is the differential dv. Okay, so this will be dv and this will be du. So let's write it that way. Okay, and now we have a very common way of writing the integration by parts technique. So the idea is given an integral, we want to splice up. We want to piece together in a product some piece u, some expression u that's easily differentiable, and some piece v that we can integrate, some piece dv that we can integrate with respect to x. And the idea is that we integrate and we'll get the u. We still have the u, we have the v, so there's that. And then over here, we're going to have a v that hopefully in integration doesn't get too much better, because integration tends to make things more complicated. But there's a few things that don't get more complicated with integration. E to the x doesn't get more complicated with integration. Sine and cosine kind of just flip back and forth, so they don't get particularly complicated with integration. But differentiation can have a way of making things simpler, especially with polynomials. So let me show you an example. All right. So our example is the integral of x e to the x. That is not something we could do up to this point. There's no substitution for that, nothing. Okay. But now we can do this problem. We can do this problem. All right. Because what we're going to do is we're going to pick our u and our dv to envision this. Now remember, the u is something that we want to either stay stable or actually get less complicated as we differentiate it and it becomes a du. So what is that going to be? I'm going to let u be x. And then that means everything else in here is going to be the differential dv. So it's going to be to the x dx. Okay? Now the next step is to figure out what du is and what v is. Okay, so we're going to have to take a derivative and we're going to have to take an antiderivative. So let's do that. So what will du be if u is x? Well, I'm just going to say it. I'm not going to tease around with that. Now, if dv is e to the x dx, what's the antiderivative? What's v going to be? Well, the derivative and the antiderivative of e to the x. E to the x is one of those functions that hands you right back the same thing. So it's what? Make sure I'm in there. Is escape e escape to the x. Okay? Now we fill in this thing up here. We fill in these pieces up here. All right? So what do we get? Well, let's see. U times v, that's e to the x, that's x times e to the x, right? Minus v du, e to the x, and then du is dx here. So here's the integral we started with, and notice that this thing, well, it's just an expression here. We're not worried about that. And this thing we can do. What is that? What is that? Well, that's minus e to the x. And then now we get our constant, plus a constant. So what we've got is that the integral x e to the x dx is x e to the x minus e to the x plus c. We could factor out an e to the x here and we'll get x minus 1 e to the x plus c. Let's see what Mathematica says that's going to be, just to make sure that, that it knows better to agree with us, because we're not playing. We'll check ourselves, or we'll check Mathematica and see if it was programmed correctly, because we know we're right. Oh, sorry, that's not the thing we're integrating. We're integrating x. And by the way, capital E is what you use. I see people using little e. Either use the funky e or use capital E. Capital E is a fixed constant in Mathematica that stands for Euler's number. So we are integrating x, e to the x, and we are integrating with respect to x. Bam. Now it never puts the plus c there, but you know better. You know that there's a whole family of things that work. I hope that helps. It is beautiful. Check out in the text, because now we have the power to figure out something that I just kind of was missing when we were doing the exponential and logarithmic work, and that is, what is the integral of the logarithm of x? What is the antiderivative of log x? We can do that now using integration by parts. Look at that example in Stewart and make sure you know how to do that. Look forward to seeing you in class and hope that helps.